All right, I think we can get started. Welcome to today's talk in the Social Science Stage Lab series. My name is Ruben Bach, and I'm happy to welcome today Achim Ahrens, and he will talk on robust causal inference using double debiased machine learning, a guide for empirical research. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research that provides a platform for researchers to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. Our presenter, Achim, is a senior researcher at the Public Policy Group, ETH Zurich, and the Immigration Policy Lab of ETH in Stanford. He holds an MSc in economics from University of Edinburgh and a PhD in economics from here at Watt University. He has worked on empirical projects in a wide range of fields, including housing economics, migration, and labor economics. And he has a strong interest in the intersection of causal inference and machine learning and algorithmic fairness. In his talk today, Achim will present a guide for empirical research on double debiased machine learning, which is a supervised machine learning estimator. And these estimators are increasingly leveraged for causal inference. One method that has received much attention is the so-called double debiased machine learning, DML estimator, which allows leveraging generic supervised ML for the estimation of common causal parameters. Achim will provide a short introduction and a guide for using DML for empirical research. Before we get started, some logistics. First, a disclaimer. We are recording this live stream in active speaker mode, which means audio from on-site and remote attendees will be recorded. And if your video is on while asking a question online, your video will be recorded as well. For those joining us online, you may ask your questions by raising your hand or posting your question in the Zoom chat. I will then read it out for you. Achim said he's happy to take questions at any time, so please feel free to ask him. And now the stage is yours. Thank you very much.
Cool. Thanks, Ruben. Thanks for having me. So the idea of today is to introduce and discuss double debiased machine learning. I spent quite a bit of time on motivating why this could be a method that is interesting and useful. And I try to make this as simple and intuitive as possible to take sort of the technicalities out of it. This is joint work with Viktor Chunchukov, Christian Hansen, Damien Kosbur, Mark Scheffer, and Thomas Freeman. More specifically, this is classic. Yeah. More specifically, this is based on two papers that I tried to mix together today, just to say that right away. One is more leveraging double machine learning, which is now coming out in the Journal of Applied Econometrics. And the second is sort of this robust causal inference using double machine learning guide for empirical research. So the second paper, which we are currently starting to write, is sort of trying to be more like a review and a guide for researchers. And so I'm really looking forward to also hear what you're interested in, what you find important, what you find interesting, and where you have questions, because we want to make this accessible to a wide audience. All right. So as I said, I will spend quite a bit of time on the motivation. And again, feel free to ask questions at any time, especially when you like some jargon that is not clear or anything, because that can obviously always be helpful for everyone. So on very high level, I mean, researchers are often interested in like one parameter or just a few parameters, summarizing, say, the relationship between one set of variables and another set of variables, and the outcome. So that would be typically that could be the average treatment effect of a language program or the average treatment effect of a minimum wage. That could also be the gender wage gap, as we will discuss later as one of the applications, which is not really like a causal parameter, but is still a very policy relevant parameter. And identification and estimation of these parameters for them to be actually meaningful often depends on some other part. And I refer to this sort of in a very abstract way of this sort of high-dimensional nuisance parameters, right? And that sounds fancy, but it's really just like that. Typically, we talk about like some confounding variables, some control variables. It could also be like, if you think of this as an instrumental variable settings, this could just be your instrumental variables. And this high dimensionally aspect, to explain this, could arise either because I have like lots of confounding variables that I have to account for, or because I just have a few, but they enter my model in a sort of nonlinear way, right? So this might be abstract, and I will give you some examples. Yeah, but really the main start from the motivation is there's something we are interested in, and as sort of like a policy relevant parameter. That could be causal parameter, that could be sort of, and there's something we don't actually care so much about, but which we need, right? And yeah, let me give you some examples, and some of them are from have an economics background, so some of them come from economics. There's, for example, this paper by Du et al., which asks whether employers have market power, and they what market power, from economists just means like they can pay below the actual productivity of a worker. And why is this relevant? Because this is for one of the, if you have market power, it's one of the justification for having a minimum wage in the first place. So it's a quite policy relevant parameter to look at the question, like, do employers have market? So what they do is they use data from Amazon Mturk, where like employers or like people interested in someone doing something for them can just post a task. They give some information, they put like a payment, like a reward, and then people can accept, or workers can accept or not accept, right? Now, maybe we should make this a little bit smaller. How does this work again?
I think if you click on more on the right, you can hide the panel.
Yeah, or was it hide? Was it one?
No, one below.
Yeah. So what they are interested in is essentially this parameter eta, which is sort of the labor supply elasticity, and which is a measure of market power. So they regress the duration, which is how long it takes for a job to be accepted, on the reward, so how much is being paid for a particular task. And the simple idea is, if, say, someone puts like a very low reward, you would expect it to take potentially very long for someone to accept it because it doesn't look very attractive. If it turns out that with the price, actually, the reward doesn't matter much, that actually this eta parameter is very small in absolute size, that means that people tend to accept whatever they can get, which means that actually the employers have market power. Yeah. But for this parameter to be meaningful, right, you need to account for the fact that the tasks are very different, right? It could be a complex task, it could be an easy task, right? You need to make them comparable. And for that, we have this X. That's our control variables, our confounders, right? And the issue here is X comes in form of text. So that could be like, that's the title of a task, and that's sort of a description, like, could be like 100 words, 200 words, what the person is supposed to do. And we want to account for that. We do that later. But the issue here is that that's a complex issue, because actually, like, how do you account for the text? I mean, like, many of you have experience with text and so on. You use bag of words, you can use some embeddings from a large language model, but there are technical issues, and this is where double device machine learning will help. I give another example, which is rainfall instruments. So there's a literature, especially in political economy, which uses rainfall instruments as sort of exploiting it as exogenous variation. Here in this paper, they ask whether political unrests that occur on a local level, like in prefectures in China, have an effect on local demand for AI technology, in particular facial recognition. The idea being, if there are unrests in a particular municipality in China, that the public, the public administration buys facial recognition software. Yeah. The issue being obviously sort of like you could have like a reverse causality because AI, if there is AI technology, if there's facial recognition technology, could also, already reduce the propensity for people to engage in unrests. That's why they use like rainfall instruments, which essentially the idea is they provide some exogenous variation that people tend to not unrest or not go on the streets if the weather is very bad. So you take rainfall, you take also thunder and wind and etc., and use these as instruments. Again, we have a high-dimensional problem in the sense that you could have many instruments. How do you specify, which climate, which weather variables are you accounting for? Which should you take, and how do you specify the exact link between, weather and unrests? Okay. Third example that I briefly mentioned already, so gender gap in wages, which is obviously a very policy relevant parameter. And we distinguish between an observed gap, which is just like, the average gap that, the average wage of men compared to the average wage of women. And then there are a couple of like a huge set of variables that partially are able to explain some of these differences, which could be skills, education, industry affiliation, experience, etc., etc., etc. And essentially the idea here is to estimate how much is unexplained in this gender wage gap. And the idea that might be, some of this might be, for example, due to discrimination. So this is a policy relevant parameter. And again, we are facing the issue of having to deal with these many x's. So these are my three examples. Is that clear so far? Yeah. All right. Yeah. All these examples have in common. There is a low-dimensional parameter of interest, and estimation of this parameter, the credibility of the identification strategy depends on high-dimensional nuisance and high-dimensional nuisance component, right? Okay. So recently, to deal with these issues, methods have been suggested that leverage supervised machine learning. And obviously, supervised machine learning, like traditionally, or like the main purpose is to predict or to classify, right? So it's not a causal method as such. But some methods essentially leverage the strength of supervised machine learning for causal inference. And one of the main methods, which has been become very popular, is double debiased machine learning, which is really like the topic of today. Why will we use machine learning in the first place? It promises to predict the future and detect nonlinear patterns in a data-driven way that you wouldn't, as a reader yourself, be able to identify. And it would, it often detects effects that you wouldn't necessarily find with OLS, or that you wouldn't capture with OLS being a linear. I will put that away again. However, this is sort of like the optimistic view, but there is a pessimistic view. And if you look at some of this, the selected papers that have looked at how well this sort of machine learning based causal inference method do, there are a couple of papers that raise concerns. One example is this Goller, Lechner et al., who look at random forest and matching, and they find that it can lead to misleading results. There is this Wüthrich and Zhu paper, which I will talk a bit about later, which essentially finds that lasso, which is a method to select control variable or to select features, and in our context to select control variables or to select instruments, tends to under-select controls, and which leads to limited variable bias. So they argue that the performance is. And then Ahrens and Franz, they look at, among others, they look at IV, and they find that, or they conclude that machine learning methods seem ill-suited for sort of this type of IV problems that I've explained, like the rainfall instruments. Yeah. So, but I will address these concerns, and I'll explain at least one reason for why we think this often happens. Yeah. So yeah, what do I do in this talk? I will review double machine learning. I will highlight the importance of selecting and validating machine learners that we use to do double machine learning. I discuss pairing double machine learning with stacking, or called model averaging or super learning, which is one of our sort of proposed solutions to the aforementioned concerns. I will go through a couple of applications, like I talked about sort of the general wage gap. So later we'll actually estimate this. I'll formulate some recommended practice, and I will also in the end point you to our sort of state and R packages that we put together to let you implement all these things relatively easily. Okay, so I will start with like the simplest case, which is the partially linear model, where really it's like not much equation. Like try to keep things simple. We have our outcome here, we have our treatment, that's our parameter of interest, and that's our control variables, right? And that could be that's exactly like for example, the monopsony application, where this is sort of the descriptions of some tasks, right? And this would be sort of my labor supply elasticity. Or so if I wanted to estimate this, what's typically and quite often done, and like obviously depends on your field, but speaking a little bit applied economics, we just assume linearity. We just say like, oh, this is linear, that's fine. Do linear regression and we're done. And that's what's commonly done. And we try to argue against that. First, I want to make an important distinction here. So what I have here is sort of this assumption of like, well, call exogenality, call it like unconfoundedness, that essentially says like my treatment conditional on these axes is like as good as random, right? And this is an important assumption because it's like an identifying assumptions. I need that to estimate this parameter. However, if, as typically done in sort of applied work, I say, well, this is linear, then I make an assumption which is purely an assumption of convenience. There is no like, there's no theory that would tell me really like this should be linear, right? You can motivate this through theory, but doing that is difficult. And we just argue it's not, that assumption is not needed with methods such as double machine learning. Why would we use something else than least squares? Well, this is sort of, I already sort of tried to explain this already, like we might have many controls, we might have many instruments, in which case it's difficult to pick which ones are important. And if I would just use all of them, that would be quite inefficient and it might not even be identified. And nonlinear effects. There's a third point which I will get to, third motivation, which I will get to a bit later when which is about the interpretation of this parameter as what is called weakly causal estimate. But I'll explain this a bit later when we have proceeded a bit more. Now this looks fancy, but all is simple. Like I can express this parameter tau using as follows. Like this is how, using this sort of my moment conditions, which is based on my unconfoundedness assumption, I can express it as follows, which is essentially, I've got my outcome here, I've got my D here, my treatment, and all I'm doing here is sort of what would be a residualization. And you just mentioned Frisch-Level theorem. Essentially, this is like Frisch-Level theorem. I could now, if I would assume linearity, that would just mean I residualize my outcome with all the x's, I residualize my treatment with all the x's, using OLS. But now the idea is I don't need to use OLS, I can use machine learning, right? And that's really very much already gets kind of close to the idea of double machine learning. Is the idea, well, my tau depends on this stuff, conditional expectation functions, right? Y given x, expectation of y given x, and expectation of d given x, right? Usually I would say this is linear, but I don't have to do this. I can actually, because this is a predictive task to estimate this, so I can just use machine learning. right? Supervised machine. Okay, so idea, I use machine learning to estimate conditional expectation functions. And these are the nuisance components, the nuisance functions, right? And there is unfortunately a problem with the idea, right? If I could just, if I would just do that now, I just, I have my sample, I have my 1,000 observations, I have my outcome that's observed, I have my treatment that's observed. I estimate this using, machine learning. I plug this in, I calculate this. I introduce an overfitting bias, right? And we can actually do like a simple simulation and actually look how this looks like. So here, doesn't matter, like it's just a simulation, but like this is sort of my 0 is my, that's my true value, right? This is my bias. And if I look at the red one first, if I just do, take like one sample and do machine learning on that one sample with, to estimate y given x and d given x, and then calculate my tau, I get a huge bias. Yeah. And this is just here, I use gradient boosted trees, here I use feed-forward neural net. Doesn't matter, you will find similar bias with many like machine learners. The reason for this is, yeah.
Can I ask a quick question about the formula on the last slide?
Yeah.
Right, so here, do we strictly assume that D is a binary treatment or that it has a constant linear effect if it's a continuous one?
Yeah, so here I haven't said anything about B being binary or continuous, so D might well be continuous, yeah. But in this setting, I would assume there's sort of like a constant effect. But yeah, we could relax that, right? This, I will talk later a little bit about like other target parameters and other models, but the partial linear model, like it's just simple, it's easy to explain sort of what's going on, what we're trying to do. Okay, so if we would just use like machine learning, supervised machine learning to estimate our conditional expectation functions on one sample, we get this bias. And really, that's the whole same like kind of overfitting issue that you would find if you just, like if you see sort of you have supervised, you have like a classification or prediction task, you obviously find it like usually prediction performance gap between the training and the holdout sample, right? And what we find here is that because you are estimating two conditional expectation functions, the estimation error between those two might be correlated. And that introduces this bias. What double machine learning then suggests is just something quite simple, which is two samples. Yeah. That is, in the simplest case, we take one sample to estimate the conditional expectation functions and the other sample to estimate the parameter of interest. Yeah. We can generalize this by flipping everything around. So we could then take sort of like, we have two samples. I'll show this in a second visually, but say we have two samples, we take one to estimate the conditional expectation functions, the other to estimate the parameter of interest, and then we flip this around, right? We take the other sample to estimate conditional expectation functions, and then the first sample to estimate the parameter of interest. And we have two parameter of interests, and we could, in principle, we could take the average. Yeah. But I'll show this in a second to you a little bit more detail. So double device machine learning relies on sample splitting, and it relies on what's called name and orthogonal moment conditions. I'm not going to go into detail of that, but the idea is essentially we need to have a type of moment conditions, which refers essentially like sort of to this part here, that is relatively robust to these perturbation, to the noise, to the biases that comes with estimating conditional expectation functions using machine learning. Double device machine learning is very general in the sense that we can essentially like use a large class of machine learning algorithms, so like those that we like, I guess, typically use, which is like regularized regression, which is gradient boosting, which is sort of neural like deep learning methods, and they only need to fulfill a relatively mild convergence rate requirement, and we are fine. And that makes this method so general. Yeah. So essentially, you want to estimate your causal parameter, and you can do it using Lasso. You can use it deep learning. You can use it, whatever, using gradient boosting, which then leads to the question, which one should I use? And that's something we'll discuss later. And it can be used to estimate various target parameters. Beyond the tau, we can do this in an IV framework. We can think of average treatment effects, local average treatment effects, and so on. So let's just quickly just review this cross-fitting algorithms. So we have our sample, it's like the full sample, which is called I, and I randomly split this into k folds. And you might have heard this already in the context of cross-validation, and conceptually it's totally the same. We just call it cross-fitting instead of cross-validation because in a way the purpose is different. Cross-validation, you want to validate, you want to sort of estimate the mean squared prediction error or the sort of the loss of a particular learner. Here we want to just estimate the condition expectation functions and then put them into our causal method. We then fit our condition expectation function estimators iteratively on the sample, excluding the first fold, the second fold, third fold, etc., and then estimate sort of the out of sample prediction and the out of sample predicted values. Let's see this. So visually, we have our full sample. We split this in this case into 5 folds randomly. So if you have panel dependence and so on, we need to think a little bit about it, like how we want to do that. But that's I'll leave that topic aside for a second. And we have our cross-fitting iterations. First, we hold out this one, then this fold, then this fold, then this fold, and then this fold. I fit my machine learning algorithm, my supervised machine learning algorithm on this part of the data to estimate, in this case, y given x. I will have to do the same to d given x as well. And I get my holdout predicted values, and at the end, if I iterate over my k folds or over my 5 folds, I have for each data point, I have a predicted value for y given x and for d given x. Yeah.
So you use the same data for both y, x, and dx?
I use the same axis. Yes. I would use the same axis. Obviously, the outcome is different, but yeah.
And then, you have your full sample. You just do the splitting into the 5 folds, and then okay.
And then I could go back here. I can go back to this expression. I can calculate the residuals, y minus y hat. That's the cross-fitted y hat, and the cross-fitted d hat. And I calculate this, and I get my sort of double machine learning estimate. Question at this point? Is that clear? Yeah. Now, the nice thing is, so I've talked about the partial linear model, but the framework is much more general. Because this pattern that I've sort of described, that you have a low dimensional parameter of interest, and then you have some nuisance stuff that you don't care about, but that you have to account for, that's just very general, right? So essentially, I just have to formulate a moment condition. That moment condition has to be name orthogonal, what's called, which is again, details are, I guess that's not I guess the intuition here is important, really. We need moment conditions that are sufficiently robust because of the biases that come with machine learning algorithms, right? But that's really a mathematical property to really understand which moment conditions are valid and which aren't. So the general framework accommodates, and these are just examples, right? The partial linear model, I've already talked about this. That would be average treatment effects and average treatment effects on the treated, right? Difference here is that, we allow for unobserved heterogeneity in terms of we could have heterogeneity in our tau. Average treatment effect on the treated is in particular interesting, for example, when you're estimating the gender wage gap. We could estimate local average treatment effects. So say you have an encouragement design where you invite people to randomly invite people to participate in a language program, and they can decide whether they want to go or not. So that we are interested in the complier or the local or the complier average treatment effects. But where you have, say, flexible controls, so where you are, so this randomization is only credible conditional on some axes. That would be a partly linear IV model with flexible controls. So say you have you have just one or a few known instruments, but again, the instrument is only credible conditional on some controls. Fully flexible IV estimation, that will be where you actually estimate optimal instruments, as in the rainfall application, AI and unrest in China. And also, if you have difference in difference estimations, so if you're familiar with sort of the recent different literature, which focuses a lot of sort of on heterogeneous group effects, essentially. If you have controls and your parallel trans assumption is only credible, conditional on some controls, then again you could use double machine. Yeah, again, the framework is general. I think I've highlighted this in the sense that all these target parameters depend on some, condition expectation functions, and these condition expectation functions you can estimate using machine learning. Good. So now, sort of I sort of essentially already said, like you could in principle use any machine learning, almost any machine learning algorithm to estimate your condition expectation functions, as long as they, satisfy a sort of a convergence rate requirement, which is relatively mild. But that also raises the question, which one should I use, right? Should I use the lasso? Should I use gradient boosting? And then should I use gradient boosting with tree-based gradient boosting with a tree depth of 5 or of 20, etc. So then now you get into all these practical issues, and we actually want to find out that this is quite important. So which machine learning performs best in a particular application really depends on the match quality between the machine learner and your data, right? And unfortunately, we don't really know which if your data set you won't know which machine learner will work best. I mean, there are some heuristics. You could say, oh well, I have many I have lots of dummies, or I have lots of variables, and I think as linear, and maybe the lasso will work better, or you think you have interaction effects, and you might work better with sort of a tree-based method. And there's really no general answer to which one is best, because in the end it's the match between the data generating process, which you don't know, and the choice of machine learning algorithm. That relates with the no free lunch theorem in machine learning, which is essentially you could have for one particular data generating process a highly specified machine learner, but then that machine learner will not work as well in another context. And the other aspect, which is really this tuning aspect, many machine learners require tuning. Depend on many. It's not like linear regression where you just run and then that's it, but you need to think about tree depth. You need to think about what's your learning rate, etc., etc. When you talk about neural nets, how many layers, how many neurons, etc., etc. And especially in sort of applied economics, the lasso has become a very popular tool, but then it relies on the assumption of sparsity, linearity and sparsity, right? Sparsity is nice, it's intuitive, because you think of there are many variables, and we like the idea that there are only a few that are relevant and that you can interpret them. It's nice because it's computationally cheap, and it has also some practical advantages, sort of in panel context where linearity is particularly nice. But there are drawbacks. What if sparsity is not plausible? What if there is not the few variables that explain reality, approximate reality? Right? There's, for example, this paper delusion of sparsity, which criticizes the idea and looks at a couple of data sets, and they argue that they find that sparsity in many typical economic data sets doesn't hold. In the end, there is a wide set of machine learners at our disposal, and it's not clear which one to use. So we essentially make the argument in favor of model averaging, or what we call stacking, which is just to combine multiple machine learners, multiple condition expectation function estimators. And the novelty here is not so much theoretical, but it's just a practical recommendation. What is, I think, in our view, a good thing to do, because you want to have, when you estimate your tau, your general age, whatever, you want to be robust to all sorts of different nonlinear effects, and you want to be sure that you hit the truth. The idea is to construct a weighted average of candidate learners. So that is, we say, well, OLS might be in there, right? So maybe the truth is linear and everything is fine, so you just use OLS. Then you use lasso, maybe you add some polynomials, then you use a random forest, gradient boosting, neural net. You consider multiple different settings. You put this all into one, double machine learning model, and then you get an idea. You get something which is supposedly very robust against different types of data structures or confounding effects. The nice thing about stacking is that it performs asymptotically, at least as well as the best performing candidate learner. So you have your set of candidate learners. Maybe one is would be the best, and stacking would asymptotically pick or put a very high weight on the best performing learner. Yeah. Model averaging techniques are not new. They are again, coming from economics, they are very popular, especially in time series analysis. When it comes to predicting GDP, future GDP, etc., or future time series outcomes. But in our view, in the causal inference context, they are still underused, and that's something we try to pose to change. Well, one exception is the use of target maximum likelihood, where Van der Laan was also advocate for stacking, and target maximum likelihood is actually a method that is this is very similar to double machine. So in the following, I will illustrate that stacking safeguards against ill-chosen and poorly tuned learners, provided that we really use a generous and diverse set of candidate learners. So the important thing is really we need to have a diverse set of candidate learners to really cover a spectrum of different data generating processes. So again, I will try to first there are the formulas, but I will try to show this visually again. All we're doing now is essentially in each cross-fitting step, we fit a stacking learner. Yeah. And this stacking learner is essentially, we have our outcome here, we have our weights, and each of these are predicted values from a machine learner. And these are the weights, there's a weight assigned to each of the candidate learners. Typically what we would do is to say, we impose that these weights sum to 1 and are non-negative, so that we get a nice, weighted average. We could also, there are, philosophical difference whether you should have non-negative constraints, whether they should sum to 1, whether you should just drop this. In our simulations, we find this combination of constraints to work quite well, and it seems quite intuitive. One nice thing is that this also is a form of regularization, and will tend to kick some of the candidate learners out of your stacking algorithm, right? So we'll tend to assign 0 weights to some of the candidate learners. So how would that in principle look like? That's now going back to my double machine learning algorithm, but now I do it together with stacking. So I have my full sample again. I have my cross-fitting iterations, 5 folds. I start with the first one here. I take these This is my new training sample now in this step, in the fifth step. And within this training sample, I do another split. Now just for visualization, I take now 3. So I do a cross-validation with 3 faults. And now I do cross-validation. Again, I get I train on these 2 faults and get out of sample predicted values. So for each, in this step, for each data point and for each candidate learner that I consider, I have now predicted values. And I continue doing this. So for each data point in my initial sort of cross-fitting iteration data set, I have now predicted values. And I use these to calculate my stacking weights. And I do that in the next iteration as well. So now we have 2 layers of sample splitting. 2 layers of, the first one is the cross-fitting iteration, where we have split into 5. Here we split in this example into 3. And we need to do that to essentially estimate these weights, which tell us which learner is doing well and worse. Right? Is that clear? Now, what's an issue with this, obviously, it's computationally extremely complex. Yeah, because we have our 2 layers, we need to fit K times V times J learners, where K is the number of cross-fitting faults, V is the number of cross-validation faults, yeah, which we need to estimate the weights, the stacking weights, and J is the number of candidate learners. Now, say we have our 10 candidate learners, and then we have 5. What did I have here? 5 cross-fitting faults, 3 cross-validation iterations for doing the stacking, times J number of candidate learners. So this explodes very quickly. Yeah.
It's also problematic if you don't have a large enough n, right? So if the sample size is just 100 or 200, it's splitting them.
Exactly, this is at this point. You might have a very poor performance in small samples, given that learners are essentially fit on, it's very small part of the data. Yeah, so you can already see, how this is all my data, and then I, in the end, only estimate this on these 2 little panels. Right? That's totally right. So what we then to simplify this whole stacking procedure, we suggest to take a shortcut by training the final learner just on the cross-fitted predicted values, right? Again, we make sort of the similar constraint on the weights, but now these guys here are just the cross-fitted predicted values. Let me show this visually again. So here you can see this all looks much easier. We do again our cross-fitting iteration. We get for each of the learner, we have our 3 learners. Get the predicted values, get that for the full sample, and then at the end, we take so here we're estimating y given x. We regress y against the predicted cross-fitted values of each of the learners to estimate our outcomes. Yeah. So outcome, these are my cross-fitted predicted values. These are the weights. I put the constraints, and that's what we call short stacking, which makes it much easier. And in line with what you were saying, now we're actually estimating always fitting our condition expectation function estimators always sort of on, in this case, 4/5 of the data. So now we wanted to figure out whether doing this shortcut, even though sort of initially one would think you have to sort of go with these 2 layers. If you take sort of the idea of stacking and double device machine learning strictly, we wanted to understand whether this performs actually well. We can do short stacking. So to do that, we did a couple of simulations. We took an original data set, sort of It's like one of these standard data sets which is often used in economics, where one is looking at the relationship of wealth. And the effect here, the treatment is sort of 401k eligibility. That's a pension system in the pension program in the US. And we control for age, income, etc., and a couple of like education, family size, home ownership, etc., etc. Now, what we do with this data set, we essentially do a calibrated simulation where we try to enforce or reinforce the particular patterns in the data. One time we essentially fit a linear learners on the data to have a fully linear model, and one time we use gradient boosting to have a nonlinear model. Yeah. So essentially we just like sample from the data and reinforce either the linear or the nonlinear patterns of the data. And let's look how this looks like. So this is now the bias and coverage rates in the linear DGP based on sort of the original data. And well, looking at sort of the bias and the as a median absolute bias and this coverage rate, OLS doing very well compared to, say, here we're using rich with like an over-specified you know, we add sort of to the controls, we had like 10th order polynomials of income. So it's like just to have like something which is like totally overblown in a way, and that seems like to perform very poorly. Also here, if you look at the neural net, in this case, we just took one example here, performs very like, you know, as is often, if you don't tune your neural net very well, like it might perform very poorly. So that is also not useful. But it could like ex ante, like you don't know which one is doing well and which one is doing well, and that's why we use here at the bottom stacking. Here I use sort of the constraint least squares where the weights are to 1 and are non-negative. And here I use single best, which means stacking only picks one candidate learner. And we see sort of like the performance is pretty much similar to what it is. Indicating that sort of like stacking detects or less being like the ideal learner. Now we have the nonlinear DGP, and I've created this nonlinear DGP using gradient boosting, this low regularized gradient boosting. And what happens again, like gradient boosting does very well because it should, because it corresponds to the truth, whereas OLS does perform very poorly. Right? And now looking at stacking, it performs like not as good, but almost in a larger sample, almost as good as gradient boosting. Yeah. So in a sense, from these two examples, we can see we don't know the truth in the end. We don't know whether we have a linear or nonlinear DGP. But if we are specifying a wide set of base learners, wide set of candidate learners, we are more likely to capture something which is like close to the truth. Right? And we have in the end something which is more robust towards like nonlinear confounding patterns. Now we can look at the stacking weights, and we can now compare like sort of the regular, the proper stacking with the short stacking, like the shortcut we are recommending, and we actually find that the weights are very similar. In this case, in stacking, we are taking the average of the weights across the iterations, the different iterations that we have to do. And so here, panel A, we see the we have linear DGP, and there's much weight on OLS. Also, some of the other like Lasso and Rich, they get some weight, which is fine. And in the nonlinear DGP, where gradient boosting corresponds to the truth, again, we have like most weight of gradient boosting. If we would use, so this is with a smaller sample, if we would use like a larger and larger sample, essentially this weight would converge to 1. And this is sort of like really in practice, researchers rarely know the functional structure in their data. And stacking and short stacking assign high weights to the data generating learner, to the true learner. Right? The nice thing about like these stacking approaches that they reduce the burden of choice by allowing us to simultaneously consider multiple learners. And which is for good news for us, this sort of short stacking, so taking this shortcut doesn't lead to like deterioration of performance. We see like a very similar behavior, and at the same time, we have something which is computationally much easier. And we also wanted to look at sort of what happens in very small samples. And so here now I looked at sort of 9,000 to 99,000 observations, and we were worried that, so because machine learners are often designed for very large data sets, we were worried that like if you have small samples that the performance might be very. And this also relates to sort of this Wüthrich and Zhu paper where they demonstrate that PDS lasso suffers, so just using lasso suffers from like significant small sample bias. So PDS lasso is a technique that is similar, like that similar to double machine learning. It considers like focusing on the partial linear model. It considers both condition expectation functions, so d given x and y given x, and you take the union of uncontrolled selected in both steps. Yeah. Different from double machine learning, it doesn't use sample splitting, but it uses like a quite strong theoretically motivated penalty level that is used by the lasso. So here we saw, like, I revisit some simulation results from Wüthrich and Zhu. So this is replication, and they look here at the mean bias relative to the full sample. So here they have two different specifications with OLS and PDS lasso. TWI stands for two-way interactions. So they consider two-way interactions of the controls that we have. So remember, we have sort of household size, income, wealth, sorry, not wealth, income, yeah, household income, and what else was there that I mentioned? Yeah, family size, earner status, etc. So this refers still to the same data set. And they had another specification where they consider quadratic splines and interactions sort of applied to income. So what they find here is that OLS is actually quite stable. And especially in smaller samples, lasso has like a strong bias. So it takes quite a bit of time for lasso to converge, for PDS lasso to converge. However, this is in the two-way interaction specifications. In the QSI specifications, so using like quadratic splines, it looks a little bit better. Yeah, but still here you have this case where this lasso specification has a strong bias relative to the full sample. Now we wanted to revisit the same thing with double machine learning using sort of regular stacking and using short stacking. And what we find here, so you see again a PDS lasso, and here you see short stacking, and here the picture is much better. So we have actually, relative to OLS, we have a relatively small bias. Again, the bias measured relative to the full sample estimate, suggesting that we have a much quicker conversion. So in a sense, what we find here is that actually considering the wider set of candidate learners seems to have made a difference in this example, suggesting that just using the two-way interaction specification seems like ill-advised. Here we consider, again, the simulations, but now we go back to the fully simulated, calibrated simulation study where we know the true parameter, where we know the true effect. And again, so here on the left, we see PDS lasso. This is linear DGP. This is stacking, and this is short stacking in red. And here you can actually see that short stacking, for the reason that you mentioned earlier, because the training samples are even smaller, actually performs better. Yeah. And here a similar picture if we have a nonlinear DGP. So we find that in a wide range, linear or nonlinear DGP, especially double machine learning with stacking performs with short stacking performance very well. All right. Questions on this one? Yeah. Good. Then I will talk about the applications to make this sort of a little bit more hands-on and like talk about like how we can implement this and how we can apply double machine learning in practice. The first one is the monopsony in the labor market that I mentioned initially. So it's like, I think it's generally a very interesting application, and like in the sense that it uses online digital trace data, and they are attractive, or it's a setting where double machine learning makes a lot of sense because you usually have like lots of user statistics and user data. Sort of have like information of what each user on this platform does at any point, so you can condition on that. But this data often comes also in very unstructured form, so that could involve text data, etc. And sort of this unconfoundedness assumption, or this assumption that you can identify your two parameter, your tau, your target parameter, is, I guess, in many settings reasonably credible because it's like a sort of you're in a kind of isolated environment where you can observe it. Okay, so as a reminder, the parameter of interest is the labor supply elasticity, a measure of market power. Outcome is log duration. Treatment is the log of reward. Remember, duration is sort of how long does it take for a job that has been posted on Amtrak to be accepted. Reward is just like how much is being paid. And then we have like controls as a mix of textual variables, so like the task title, description, and keywords, and non-textual variables, including the time allocated for the task. So you give like an estimate how long it will probably take, required qualifications, and then there are a few other like information to measures of the type and the complexity and attractiveness of the task. But especially the title and the description and keywords, they come as texts. So what the original authors do then is they use sort of a mix of keywords, topic modeling, and word to vector embeddings. And this is sort of like we replicated their results. But using sort of this our short stacking and stacking. Again, so now we consider a wider set of candidate learners, OLS, CV loss, so CV rich. So cross-validated loss, so cross-validated rich, random forest with relatively low regularization, random forest with high regularization, gradient boosting again with low and high regularization. But you could expand on this obviously with different and multiple different parameter settings. Okay, so now if you look at sort of column 2 to 8, you will see that some of the coefficients are very different. So if you just would consider OLS, you would have been naive with like these tons of controls, you would have got an elasticity of 0.379. Quite similar for Lasso and Rich. These random forests, like the coefficients are a bit lower in absolute size. So if you take these at face values, right? If you don't account for like considering also your gradient boosting in this case, this would suggest that if you change the wage or the reward for a task, that workers are very responsive to it. But in the end, if you actually, because we have so many controls, we here now use gradient boosting with just different settings, it drops massively. Suggesting that they are not very responsive, so that there is actually market power, right? Now you will be asking like, okay, which one is the right one? Because like these are all sort of kind of, plausible, like in a sense, like double machine learning estimates. But if we have a closer look, we, for example, look at the mean squared prediction error, the cross-fitted mean squared prediction error, that these candidate learners, they're not the same, right? So this is sort of the mean squared prediction error corresponding to the outcome is much larger. It's like more than double in size compared to the one we use from gradient boosting, right? Similar here, when you look at treatment, the differences are less strong, but also here you can see like this random forest does very poorly compared sort of looking at the mean square prediction. Now, if we look at short stacking, these are the weights, you see that for all these candidate learners, the weights are 0, and that all the weights are put on this. So this is a way of validating which one of these actually makes sense. And because machine learners they're not the same, right? They're not like, OLS is OLS, it's also machine learning algorithm, but there is so much variety in the random forest, and sometimes random forest does very well and sometimes very poorly, depending on the setting. Sometimes gradient boosting does well and poorly, depending on the setting, etc. So we need a way of validating which one to use, and this is sort of what this framework tries to do.
Okay.
Yeah.
So in this case, I mean, part of the data is like part of the axis is textual data, and like from my intuition, there's no good reason why we would impose like a linearity assumption. So it seems plausible that non-linear learners perform best, right?
Yeah, I mean, but I guess so. The examples in this example, linearity doesn't seem to make much sense, but there are examples where people tend to use OLS, but where it still might make sense to at least consider these other learners as a robustness check, and this is sort of what we're trying to suggest.
And one more question: Do you use the same learner for the outcome and the treatment estimation or prediction?
So we consider the same set of learners. But in the end, the stacking weights you see here, there are stacking weights for the outcome and there are stacking weights for the treatment. Now they are slightly different.
Yeah.
And we allow for that, for them to be different. And I think that's important because if you just say, okay, I use only OLS or I use only a particular random forest, usually enforce or make the assumptions that the relation, like the functional relationship, like in Y given X and D given X is the same, but there's no reason to believe that this is the case. And this is also one thing which we're trying to.
And maybe this is more towards the end, but I'll ask right away. How, like, I would train such a model from a very applied perspective. How do I tune the model? Like, do I focus on getting prediction, minimizing error, or like the main identifying assumption is unconfoundedness?
So I mean, here I report just a couple of different kind of learners, but what I would recommend in practice is to consider a wider set, and then you get like an idea of which kind of learners are doing well or not, right? So here I see kind of gradient boosting is doing well, and I consider just 2 gradient boosting. The next step in my analysis, and this is like preliminary stuff, right? I could add a few more. So what I do here, I have 2 types of gradient boosting, 400 trees. I wrote down here what I did. So the difference is the tree depth, which is 4 and 20. Now I could play with other tree depth as well, right? I could add a few more to get an understanding what is doing well and what isn't. I mean, these random forests are doing relatively poorly. So I would maybe reconsider changing the settings a little bit, because I don't think there's probably just something, that happened. These settings don't seem to work very well for the random forest. I'm sure you can make the random forest do a little bit better in this setting, but just maybe add, consider more trees, because here I just did 400. I would use 1,000, etc. Yeah, but so you can play with that, and then in the iterative procedure, like I'd start from a larger set, and then you will probably, for computation reason, like narrow it down a little bit, right? Yeah, does that make sense?
Yeah, just another quick follow-up on the textual data. I mean, you mentioned how the original, or in the original author's analysis, they ran topic models and other stuff. But now that you use a set of different candidate learners, how is this textual data processed into the axis that you feed into those algorithms? So is it always just this text string as it appears in the ad, or is there some sort of pre-processing involved?
Yeah, so there will be, so you take essentially the text strings from like the title and the description, and then you use like, and you can use word counts or bag of words. And then in addition, they used embeddings from, word to back, and then they used in addition topic one. That's what they did. What we did, and I haven't shown this here because so we used BERT as well, and it didn't do well at all. And that actually also makes a nice example because you actually, when I used BERT, and I didn't bring the results here, but it would also give me widely different point estimates. And if potentially as a researcher, you might be like, okay, stop, I'm done. And then you're like, this is my result. But it's important to validate this and to consider what it said.
So there still is like a lot of research and degrees of freedom and like modeling choices.
There are modeling choices, but we are trying at least. I mean, one thing also like it's about, considering a wider set, it's also about being transparent about what different learners do, right? And then you can also see, we have these kind of learners here, and they are not, these point estimates are not qualitatively the same, right? Because not just in terms of the point estimates, but also in terms of their validity. Because if you look at short stacking, this is what we actually get. Puts a high weight on gradient boosting, suggesting that these estimates are much more sensitive.
I've read a paper recently, Invents and Xu, I think it's a working paper, and they compared like modern tools, double-divided machine learning, for example, to experimental baselines or benchmarks. And what they found is that like when different methods, like you have here, when they vary a lot, then this indicates often that there are deeper problems in the data, in the sense that they pointed towards lack of overlap in the covariates. Is this also something you look at here?
So here I don't, we're not looking at overlap, but I'm not sure I fully agree. First of all, if you think of experiments as the reference point, we all agree that in terms of like internal validity, like an experiment is gives you much more precise and credible estimates. Well, this is like, that goes without saying. But in terms of like, I'm not sure I agree that like necessarily if you have heterogeneity in your estimates, it necessarily means that something is wrong with your data, whatever wrong means, right? Or there is some deeper issue. For once, like it could be just a specification issue that you are not validating your learners properly. The issue is then if you take clean simulated data, as I've done in one of the earlier examples, and I use a neural net without thinking much of which parameters to put, I can produce whatever estimate I want. Like it's just, they can be all over the place if the neural net is fully specified. It might just go in all directions. It might, but if you look at the performance of the neural net sort of then you often see, you can have a neural net that does worse than just having a constant, right? So yeah, so I'm not saying this couldn't indicate that there are deeper issues, but I also think it doesn't have to be that there are deeper issues.
But it's something that can be like, you can investigate it quite easily now.
How?
Like overlap?
Overlap, yeah. So, overlap for sure, yes.
I think that was the main point.
Yeah. No, to look at overlap, like generally, like especially so like we looked a little bit more at overlap in the gender wage gap application. That's a huge issue to have credible estimates of the gender. So the unexplained gender wage gap is difficult because overlap often is not very credible because there are, if you make it very detailed, if you look at small cells of people with a certain education working in a certain industry, and then you start comparing, like, even if you're a large data set, the 3 women with a certain, industry affiliation, certain education level, etc., with the 10 many men, possibly, or the other way around, then you have overlap issues. Yeah, that's. Yeah, so I mean, this goes also in the right. So I actually, before I go look at the gender wage gap, I also looked at the gender citation gap. And it is well documented that women, are underrepresented in academia. Possible reason is that, their work is subject to more sort of skeptical scrutiny. That could be reflected in lower citation counts, and that's something we look at in this application. So what we did, we took sort of like the top 30 economic journals, looked at the last 30 years roughly, and looked at the gender composition of authors. So we we took the author names, we put it sort of through a gender classification algorithm to estimate sort of the gender, and then we have outcomes of log citations, treatment is indicator for all female authorship, and we also have an indicator for mixed gender authorship. So this is an example where we have actually 2 treatments, not just one. And the controls, we use the abstract text. So that the idea being, we need some, understanding of, because men might work in different fields and there might, possibly like a gap in quality. So we need to some way account for that. And that's what we do using sort of, for simplicity, just for the abstract text. Again, practical challenge is similar, how to encode the text, how to deal with the text data. And we, again, so we use unigrams, so just like word counts, and we use BERT. And again, we find variety in differences in the point estimates. So just to explain first what we do here. So remember, so the double machine learning algorithm relying on cross-fitting, and cross-fitting means you do sort of random sample splits. So obviously, if you run with different seeds, double machine learning twice, you get 2 different point estimates. So what we actually do, and what we also suggest to do, is to run double machine learning multiple times. So here we actually do it 5 times, and then we do median aggregation. The idea being, we don't want this dependence on the fault, and if the fault actually makes a huge difference, then maybe something is going badly wrong, right? So this is possibly also a good detection algorithm. Here, the differences across, so like green corresponds to multiple double machine learning iterations, and the orange or brown or whatever this is sort of the median aggregation. So here we can start off with OLS. That's PDS loss. So these are full sample estimators, and this is actually indicates there's a strong, in this case, a strong positive effect of having a mixed gender author team. While there is a negative, here this is a 0 effect, but generally there's a negative of having an all-female author team. So this where an all-male team is sort of the base group here. So this is all referenced to an all-male team. Again, we see the variations. Again, it's not clear which of these candidate learners is the right one. And note here, I use OLS with just the unigrams and OLS with just BERT. So actually, I use the different candidate learners actually have also different control variables. Yeah, because I use different text representations. And if I would consider the neural net here, the effect would be 0. But if again, these are not the same. In terms of their validity, if we look at stacking and short stacking, this would gives us sort of a weighted average where the weights are larger because the performance is better in estimating classification functions. We can look here at the weights, and also in this application, so we have actually quite a bit of, one thing which relates to the comment earlier, you see the weights are quite different across the condition expectation functions. So this is outcome citations, this is outcome all female, this is outcome mixed gender. And the weights are quite different, right? For example, here in citations, we have relatively large weights, again, gradient boosting, but also OLS. all female, we have less weight on OLS, for example, in comparison. More here goes to lasso, etc. So there are some differences, right? Yeah. To finish up with the final application, that would be the one gender wage gap. And we look at UK. Unconditional wage gap is around 14%. A relatively small number of observations. We use a W robust estimator to estimate. So this is, we're estimating the average treatment effect on the treated. So we're assuming overlap as well. That can be a big issue. And the covariates are, whether someone works part-time, industry, education, occupation, health status, etc., etc. We have kind of continuous one, age, tenure, literacy, numeracy, score, years of education. And this is how this looks like. We consider like different set of control variables. So we want to highlight that you can actually, use stacking as well to, decide between different specifications, different sets of control variables, similar as you could use the lasso for this. And this is again what we get. And you see here, and this is better than in the previous application. For example, we have CV rich with the extended specification, and that's a specification where you have lots of lots of complexity. So the overlap assumption is less likely to actually be valid. And here we have lots of a variability across the double machine learning estimates across the iterations, yeah, which could be a symptom of like your overlap assumptions not being valid. For other candidate learners, there is more stability, and again, neural net. Again, we just like pick the simple specification, and yeah. And now we compare this to constraint least-squares and single best stacking. And here with constraint least-square, we have much more stability, and we have a point estimates which are sort of combined average across these candidate learners. So here the unexplained wage gap then. So we had the total wage gap was around 14%. Now we are here closer to I think that will be around 8%. Again, we can look at the weights. Here, much weights go to, in this case, to random forest and rich. Sorry, to random forest, but not to rich. And you can see here, random forest relatively stable, CV rich very unstable. Gets also low weights, which is what we would desire, right? Okay, so now since I'm going to the end, some of the key recommendations that we develop is obviously to use style machine learning with stacking or short stacking with a diverse set of candidate learners. And this could often include OLS, which is, I guess, for men like sort of kind of a default choice. And there nothing stops you from considering this as a baseline and including this in your set of learners. If the sample size is small, it makes more sense to use short stacking rather than stacking, and also to increase the number of folds, because in the end, you're training data. The data you use to actually train your condition expectation functions gets smaller and smaller. And I think, I think it's practically important, inspect the weights like we do here, and then that allowing you to refine your your EML specification. The takeaways are that we argue that double machine learning with stacking safeguards against ill-chosen learners, which is one of the main worries that we have, I guess, and that we want to address. Short stacking performs comparable to regular stacking, sometimes even better. while being computationally much cheaper. So, and double machine learning allows weakening these assumptions of convenience like linearity, while at the same time, we still need to be careful in specifying our identifying assumptions, right? That includes, what is a control and what is a good and what is a bad control? What is what could be a mediator or what could actually be an outcome variable rather than a control variable. Not much time, but we have put together sort of two packages to actually implement these sort of short stacking algorithm. One is for Stata, one is for R. There are some tutorials on these websites to explain sort of how this is being done. We try to make this reasonably intuitive. There are help files and tutorials and everything so that you can dive into it if you're interested. And yeah, that was it, I guess.
Fantastic. Thank you very much. We have a few minutes left for questions from the online audience or here from the room. Raise your hand, post your questions to the chat. I think we already had a lot of questions during your presentation, so I guess we are fine on this also regarding time. Thank you very much again. This was an extremely valuable presentation, at least for myself, and I hope for the rest of the audience as well. Yeah.
Cool. Thanks a lot. Thanks for coming and listening. I hope you find it interesting.
We will make sure to check out the software packages, and
Cool.
also given that I think at least among several people here at the School of Social Sciences, and then this data is also quite popular. And with that, I would like to make a last announcement for today. The next event in the SSDL will take place on October 16th, and Oliver Littmann, who's also here in the audience today, from the University of Mannheim, will teach a workshop entitled Computationally Analyzing Politicians' Body Language Using Pose Estimation. So I am very much looking forward to that presentation. Thank you once again for joining us today, and see you soon. Thank you, Achim.
Thanks.
And see you in a few weeks for other stuff.